Welcome to part 5 on solving mazes with reinforcement learning. Today we're going to put together the buffer class. So for many reinforcement learning algorithms, you don't want to you want to be sample efficient. You don't want to throw away data once you've generated it. But you also want to be able to give the agent a wide range of experiences to learn from. So you don't just learn based on the last thing you did or the last 50 things you did. You learn based on the last 100,000 or 300,000 things you did. And a lot of these things work really well with a buffer out to, 1 million plus. So we're going to be building the Python class to hold that buffer and let the agent train on batches of past data. So with that in mind, let's go ahead and get going. So this is going to be buffer.py, and we're going to need numpy, so import numpy as np. We're going to call it replay buffer. And in our init method, hang on, it autofilled a little bit too much there for me. We want self, max size, input size, and n actions. We're going to use that to calculate some of our array sizes here. So self.memSize equals max size, self.memCounter equals 0, self.stateMemory equals np.zeros self.memSize and input size, self.newStateMemory, and we're going to type all this out and then I'll talk about it a little bit more. Self.newStateMemory equals np.zeros, self.memSize and actions. And just so it's clear what I'm doing, np.zeros is going to create, that's a numpy function to create a numpy array of zeros. It's going to create it in the shape that we're passing in here. So if mem size is 1,000,000 and input size is 8, this is going to create a numpy array that's 1,000,000 by 8 for us to store our state memory. Same here. If it's going to create that 1,000,000 by 8. I'm making those numbers up for now, but you get the idea. The reason we have a memory counter is we're going to increase that counter by 1 every single time we store a value. And that's going to basically let us slowly step through and fill the memory up and know what the last thing that we added was. So let's see, new state memory, we're going to do action memory equals np.zeros, and that's going to be self.memSize again. You're starting to see a theme. And actions, self.reward memory equals np.zeros, and this is just going to be self.memSize. We don't need it to be multi-dimensional because it's just, or three-dimensional because it's just reward is going to be a single value. And self.terminal memory equals np.zeros, and that's going to be self.memSize and dtype equals bool. Now, just to double check, you should see that you've got double parentheses for all three of these and a single set for these two. These are three-dimensional, These are just a 2D, or one-dimensional row of values there. So, all right, we are going to define a function to tell us if we can sample. So we're going to say def can sample self batch size. And what we want here is if there are no memories in the buffer, or not enough memories in the buffer, we want the external code to be able to check that and just keep going. Now, obviously, we could do some of this logic in the main loop. My preference is to allow the replay buffer itself to tell the main loop whether or not you can sample from it. So we're going to say if self.memCounter, remember this is how much of the memory is full, is greater than, and I'm going to say batch size times 5. This is somewhat arbitrary, but I basically want 5 times, if you're trying to pull a batch of 32, I want, 32 times 5, I want 160 entries in there. If you were trying to pull a batch of 500, then I want 2,500, 2,500 entries in there before I allow anyone to sample, so that you're not just sampling the same data over and over again, or trying to pull less data than what's present. So that's what this is for. So if self-memCounter is greater than batch size times 5, return true, else return false. Okay. Now we need our function to store the transition, and then we'll do a sample buffer. So store transition self state action reward state to next state done. And if you look these up, this is going to be a common set of values for anything modeled after a Markov decision process. This is a pretty normal set of values to use for reinforcement learning. So what we're doing is we're effectively saying that the agent needs to know the current state, it needs the action, and it needs to know what reward was taken in that state, in order to determine whether or not that was a positive action to take. He uses next state in the same way to try to figure out, hey, what I've taken this action in this state, was the next state a good place to be? I'm probably explaining that very poorly. You should definitely look up Markov decision processes and spend some time on videos that are heavier on the theory. For now, just know these are standard, and we are going to be storing them so that our agent can train. So index equals self.memctr percent self.memSize and self.stateMemory, and we're just going to be using the index value equals state dot new state memory index. Now let's be consistent. I called this new state memory here and next state here. Let's just go ahead. I like next better. So let's change that to next. Let's change this to next. Next state memory index equals next state self.action memory index equals action self.reward memory index equals reward self.terminal memory index equals done. And we're going to increase self.memctr plus equals 1. All right. So let's talk about a little bit more about what this is doing. So for every time you store a transition, it's going to increase mem counter by 1. And then when you attempt to store a transition, it's going to generate an index from the current mem counter. So why are we doing this self.memCounter modulus self.memSize? Well, couple things. We need to, let's say mem size, and you don't have to type this out. I'm just gonna use it as an example. So let's say mem size is 100. That's your mem underscore size equals 100. All right, and I want to store a value, and my mem counter, let's see, mem counter is 40. All right, so doing mem counter modulus, so modulus, of course, is like a remainder operator. So if you do 40 modulus 100, what you're going to end up with is 40. So because it's 40 divided by 100, if you're using modulus is 0 with a remainder of 40. So that's going to come back with a value of index will be 40. So cool. Why are we doing this? Why not just directly use mem counter? Well, we're not going to directly use mem counter because mem counter at some point will exceed mem size. So what happens if mem counter is 101? Well, now mem counter modulus mem size is going to return a 1. So what we're effectively doing is filling up the buffer up to mem size, and then this little line of code is going to let us loop back and start back at 0. So last thing you might be wondering is why not just use a list, just create something of variable size, and hey, once size is greater than 100, remove a value every time you add one. And you can totally do that, and it works. The cool thing about this is that it provisions the entire, it provisions the NumPy arrays ahead of time at the target size, and it ends up being faster and a little bit more memory efficient to have already pre-provisioned that and to just cycle through and add to it and replace things than it does to have a constantly expanding array. All right. So now you understand hopefully a little bit more about the structure we're using. Let's go ahead and build a sample buffer method. So we're going to do self batch size, and we're going to do max mem equals the min of self.memctr self.memSize, so whichever one's smaller. We're going to do batch, and again that's because mem counter can be smaller than total memory, at which point memory will be the size of mem counter. If mem counter is bigger than total memory, then that indicates that the memory is full. So max mem is whichever number is smaller. That's what min's going to give us. So we're going to say batch is np.random.choice inside max mem and batch size. So this is going to grab a set of choices that is batch size large up to inside of a range of max mem. And then it's simple enough. We're going to do states equals self.stateMemory batch. Next states equals self.stateMemory batch. Actions equals self.actionMemory batch. And if this looks a little weird, again, this generated a series of indices, and we're using those indices here to select, batches of data. we're not just saying, grab me everything from 1 to 50. We're grabbing random choices from state memory and then pulling those batches back. Rewards equals self dot reward memory. Batch. And dones equals self dot terminal memory. Batch. And then we're just going to return states, actions, rewards, next states, and dones. And with that, we have completed our buffer.py. Now, something that starts to get useful at this point is being able to write some basic test cases. So we, over here, we were able to go ahead and just add our gym.make stuff to our main py, and this is something that will go into the final code base. But it's useful to be able to test things as we go and not just trust that, hey, I typed everything right, and when we get to, we'll find out in the final video if it all worked. So what we're going to do is we're actually going to create a new file called unit tests.py. And there are Python unit testing frameworks. I'm not actually using any of them here. So we're probably doing this wrong, but it's going to suit our purposes. So I'm going to, in my unit test.py, I'm going to from buffer import replay buffer. And let's set some basic variables. So buffer size equals 10. We'll say, I'm going to use a loop. So I'm going to say loop size equals 20. And we're going to say memory equals replay buffer, buffer size, input shape. Let's see, what did I use over here? Aha, input size. I think this should be input shape. Let's do input shape here. And we'll change that here as well. All right, so input shape is 1 in square brackets, an array of 1, and actions equals 1. All right. So let's see. Didn't like my input shape, probably because I didn't save the file over here. All right, let's take a look at that. What did we not like? We didn't like something, and this is why you test. This is why you make sure that the things that you're doing work as you do them. All right, let's go back to input size. Not that the variable name matters, but I actually think that maybe that needs to just be a 1. And that needs to be a 1. All right, it runs so far. Cool. We have a, at least at this point, we can create a memory. Let's attempt to use it. So for I in range, loop size, memory dot store transition, I. All right, simple enough. We're storing a bunch of i's. So again, I'm just going to run this as we go. Still working. So print testing to ensure the first state memory is correct. And we're going to assert that memory dot state memory 0. So the first state memory is 10. And why should it be 10? Well, it should be 10 because we gave it a buffer size of 10, and then we looped through it 20 times. So at this point, the first 9 numbers, or the first 9 numbers should be gone, 0 through 9, and it should, or first 10 numbers 0 through 9, you know what I mean, should be gone, and the 0th element here should actually be 10. And we're going to print test successful. I'm adding a little extra spacing, so let's run that. All right, and that ran successfully. So you'll notice I didn't do any if-then stuff. What assert does is this would have thrown an error if this was wrong. So I'm going to do a 9 here, just for kicks, and we get an assertion error. So if anything in this test had failed, the code would have actually failed. And then finally, let's just copy this, and we're going to do another one. So if we say memory, we're going to go to the -1, the end of the list, and we're going to confirm that the end of the list is 19. So last state memory. All right, and we also have a successful test here. So I think we can be pretty confident knowing that our buffer.py is working correctly, or at least working correctly based on the test parameters we've passed it, and that we should be able to go and use it, in other code successfully. Obviously, if you've got an error here, this is a great place to go back and fix it and make sure that that everything is working before we move forward in the course. So with that, I'm going to end this video here, and we are going to pick up next, starting on the agent.